In this segment, we're going to talk about counting, or more accurately, the ability to identify the probability after a sequence of events. And so to do this best, we're going to actually start with an example, and that is calculating the probability of a coin toss. So assuming you're using a fair coin and you're trying to determine if a coin comes up, let's just say heads, you can say that on the first coin toss, the probability is 1/2. The probability on the of getting two heads in two coin tosses is 1/4. On the third head, it would be 1/8 for all three of those to be heads, and so on and so forth. And so without going into too much detail here, ultimately we can define our sample space as these items here on the x-axis, the 1, 2, 3, and 4. And so the easiest way to look at this, if we derive a general formula for this probability, we can say that the probability of that nth occurrence is 1 over 2 raised to the nth power, where n is just the number. So in this case, we have a probability of 1/2, then 1/4, then 1/8. This can also be written as 1 over 2 to the first, 1 over 2 squared, 1 over 2 cubed, 1 over 2 to the fourth, and so on and so forth. Now, to take this to the next level, we want to look at trying to generalize this and say, is this even valid? And this next line of information here is really what proves that this is a valid sample space, a valid omega where it's equal to 1. You may look at this initially and say, okay, it's 1/2, then 1/4, then 1/8, then 1/16, so on and so forth. Does that actually add to 1? And this is a generalized proof that will show that. So we can say that we're taking the sum from n equals 1 to infinity of this probability 1 over 2 to the n. And if we do a quick substitution using our rules of geometric series, we can pull out that 1/2 times the sum of n equals 0 to infinity of that same 1 over 2 to the n is these two are equal. Now, pulling that 1/2 out front leaves us with, again, just a standard geometric series that we can convert using some of those rules back from calculus. So in this case, we end up with a 1/2 times 1 over 1 minus 1/2. Now, simplifying that out, that becomes 1/2 times 2, which we can say absolutely does equal 1, which means that this area, this distribution here, is a valid sample space because it does sum to 1 over all values of n. To take this next step further, let's say we want to find a probability of a specific event occurring. Well, we've already got those identified. Each event is just 1 over 2 to the n. Now let's say that we're trying to find the probability that the outcome is even. That is, that the n is actually even. Now, the easiest way to do that is to say we're really looking at the probability of a set, right? And that set is going to be 2, 4, 6, so on and so forth. Now, to do this another way, we can use our additivity laws that we developed in a previous segment to say that this right here, the probability of this set, is actually just equal to the probability of 2 plus the probability of 4 plus the probability of 6, so on and so forth. Now, substituting in the equation that we developed earlier, where the probability is just 1 over 2 to the n, we can say that this probability is really just 1 over 2 squared plus 1 over 2 to the fourth plus 1 over 2 to the sixth, so on and so forth. Which leaves us at a point where we can do some fancy math. Now, the easiest way to look at this is to pull out a 1/4 from the front of this. And what that leaves us with is ultimately 1/4 being subtracted from all of these. Or another way to look at that is 1 over 2 squared. We're taking a 2 out of the exponent of all of these fractions. And so that will leave us with a 1 plus 1/4 plus 1 over 4 squared Now, using the same rules as we established earlier for a geometric series, we can see that this is really still just another geometric series. We can go through and simplify this to be equal to that same 1/4 out front times 1 over 1 minus 1/4. Again, just pulling this base value and inserting it. Now, when we do this, we find that this is equal to 1/4 times 1 over 3/4, which is ultimately equal to 1/3. Those 4's cancel out. And this is the probability that the outcome is even. One of the things that we haven't proved at this point is that we can do this. We kind of used an assumption here, which was to say that the probability of this set is equal to the sum of each of the outcomes. And this we don't know. So far, that additive property we've only established for finite sets, whereas this is infinite. So to put that a different way, we can say that current additivity properties only cover finite sets, not infinite sets. So let's go through and figure out a way to establish that. Let's look at some examples and, more accurately, some rules that we can utilize as we establish countable additivity for infinite sets. So the countable additivity axiom basically states that if A1, A2, and A3 are an infinite sequence of disjoint events, then the probability of each of those events unioned together is equal to the probability of the sum of those events. Now, this word sequence, you'll notice I've bolded because it's kind of important, and we'll come back to why. Now, in a generalized case, we can say that maybe this here is event A1, and that this is event A2, and that this is event A3, A4, and so on and so forth. So in this case, we have discrete labels for each segment of this area, but there may be infinite. Maybe these are getting smaller and smaller as we go along. Now, let's assume this holds true for a second and look at a slightly different example. Let's jump over to a continuous example where we say we have a sample space omega that is comprised of XY pairs. And we can say from the rules that we've established already that the probability of that sample space, or the probability of omega, is really just equal to the probability of the union of all X and Y pairs. Now, the part that's in question here is, does that equal the sum of all probabilities of X and Y? Now, we established earlier that the probability of all XY points is equal to 0, of a singular point. Now, taking a step back, we also established that the probability of our sample space has to be equal to 1. So for this to hold true, 0 has to equal 1. And, well, it doesn't. So we have a bit of a dilemma here, something that we have to figure out. And so for this to hold true, we're going to establish a couple of critical principles. And the first one here is that additivity holds only for countable sequences of events. So by countable, it can be infinite series. It can be something like an infinite coin flip, but we can still assign a number or some value to each of those elements. They are what we call countable in the world of probability. Now, the unit square with all of its individual points is not countable. There's just an infinite number of points. So the question you may be asking at this point is, well, wait, how does that work with area? Is that like we used area earlier to try and calculate the probability of an event occurring within a specific space? Is that still a thing? Can we still do that? And the good news is the answer is yes. Now, the reason as to why that's a yes is outside the scope of this course. But for the purposes of this course, what we'll say is that there is a field of study called measure theory. And measure theory ultimately provides that area is a legitimate probability law for the unit square so long as the sets, the areas that we are trying to evaluate, are nicely formed. Now, again, for the purposes of this course, we aren't going to use any non-nice set areas. We're just going to work with nice set areas.